Now, what forces the electrons through the resistor? Well, as we said before, it's the voltage drop. In other words, the difference in voltage between one side and another. It's not the voltage itself, it's the drive. It's not the voltage itself is the driving force pushing current through a resistor. Now, in hydraulics, it's similar. The pressure difference between two sides of a pipe, it's not the pressure itself determines the flow through it. For example, there may be a large water pressure above a pipe which tries to push water down the pipe, but there may be an equally large water pressure below the pipe which tries to push water back up the pipe. If these pressures were equal, there's no water. So it's not just the pressure, it's the pressure difference between 2 points. So don't forget, pressure difference. Now, the resistance and conductance of a wire, resistor or other element is generally determined by 2 factors. You've got the geometry, which is the shape, and you've also got the material. Yeah, what's it made of? Now, geometry is important because it's more difficult to push water through a long, narrow pipe than a wide, short pipe. In the same way, a long, thin copper wire has higher resistance than a short, thick copper wire. Now, that's the first, that's geometry. Now, what about the materials themselves? That's important. Now, a pipe filled with hair will restrict the flow of water more than a clean pipe of the same shape and size. In a similar way, electrons can flow freely and easily through a copper wire, but cannot as easily flow through a steel wire of the same size and shape. And they essentially cannot flow. It's like having different materials like rubber, etc. What it is, it's like pushing it through a wire that's full with hair. In other words, it's not easy to go through certain materials. That's what the problem is there. The difference between copper, steel and rubber is related to their microscopic structure and their electron shell configuration, their electron configuration. In other words, how they are arranged. Now, the hydraulic analogy compares electric current flowing through circuits to water. We try and compare water going through a circuit with electricity when we try and make you understand electricity flowing. Now, when a pipe is filled with hair, as you can see here, it takes a larger pressure to achieve the same flow of water because the hair creates resistance. Now, pushing electric current through a large resistance is like pushing water through a pipe clogged with hair. It requires a larger push or electromotive force to drive the same flow electric current. So, objects such as wires that are designed to have low resistance so that they can as easily transfer current with the least loss of electrical energy are called conductors. So conductors have the ability to let current go easily through them. Now, objects that are designed to have a specific resistance so that they can dissipate electrical energy or otherwise modify it are called resistors. They're resistors. This could be a heater, iron, kettle, fridge or anything that converts electrical energy into another form of energy. Now, running current through a resistance creates heat. As electricity goes through a wire, it creates heat. And this is called Joule heating, as you can see here. Now, resistors and other elements with resistance oppose the flow of electrical current. Therefore, electrical energy is required to push the current through the resistance. This electrical energy is dissipated, heating the resistor in the process. Now, the dissipation of electrical energy is often undesired, particularly in the case of transmission losses in power lines, and that's why they transmit it at high voltage. High voltage transmission helps reduce the losses by reducing the current for a given power. So by transferring at high voltage, it reduces the current because it's current that causes the loss of energy. Now, on the other hand, Joule heating is sometimes useful. So we don't want it in high voltage cables, but we want it in other things. For example, electric stoves and other heaters, which are called resistive heaters. As another example, incandescent lamps rely on Joule heating to work. So it goes through and it creates light. The filament is heated to such a high temperature that it glows white hot with thermal radiation, which is called incandescence. In other words, that's what they rely on, this Joule heating. Now, the formula for Joule heating is P equals I squared R, where P is the power, which is energy per unit time, I is the current in amps, and R is the resistance in ohms. And this shows you that the amount of heat created in a wire with electricity running through it is proportional to the square of the current. If you double the current, the heat released is multiplied by 4. Can you see why, again, high transmission, high voltages are used rather than high current? Because if you double the current, you times the resistance by 4 on the heating. And it's also proportional to the resistance. If you double the resistance, you double the heat released in the wire. Now, as I said earlier, that's why electricity is transmitted at high voltages, to reduce the current, therefore reduce the heat losses when transmitting electricity.